Hey, welcome. Today we're going to be talking about how electric motors work. I would argue, and I think a lot of other people would argue as well, that our modern society depends on electrical generation and electric motors. So using electrical energy and converting that into mechanical energy, that's fundamentally what we're going to be talking about here. So it is crazy important as a topic if you think about all of the everyday life items that you benefit from in terms of things that would be harder to deal with otherwise if we did not have access to electricity and magnetism concepts and technologies. Motors are really just about everywhere. Alright, so let's go ahead and talk about what you're seeing on the screen right now. So this is a GIF animation here, and on the left side we have a magnet, the north end of a magnet, and on the right side we have the south end of a different magnet. So there are two static magnets off to the side, and so you could call them stators. And you've got the magnetic field shown as yellow, these magnetic field lines going from the north side to the south side of the other magnet. And what we do have is like a battery, for instance, and an electrical circuit, and you can see the charges shown in these yellow dots. Now notice the charges are not moving the entire time, and that is correct. And there is a complex thing going on in the center here where you have a rotating loop of wire. And one way to think about this is this loop of wire is going to form an electrical connection with this part of the circuit. It's going to complete with the other part of the circuit at different times. Occasionally, the connection is broken, but this thing is spinning already with something called rotational inertia. So even though there are gaps in this where there is no force on the electrical loop here, it's got enough rotational inertia that it just continues in its motion. And so our job for today is to understand how this works. And it's not easy to do, but it is crazy important. Alright, so let's talk about some of the details here, and I will come back to this concept that you're seeing right now. So the thing I want to start with is just a couple words that I want you to become familiar with. Notice that there are black squares right here. These are brushes. These are metallic brushes that connect with these blue lines, these blue arcs right here, are called commutators. So the commutators connect with brushes, and when there is a complete circuit, then the current is flowing in the wire that you can see that's extending into the page, or into the screen rather. And so you could say, all right, well, what's happening with that? Remember that when you have a moving current, then that's going to create a magnetic field around that current in like a wire. We've talked about that with the right-hand rule. I can put a link up to the upper right to right about now to help you to become refreshed with that info if you need it. But basically what's going to happen is there's going to be a magnetic field created by that current in the wire. Now, if we time it perfectly, then what would happen is the north side of this static magnet on the right hand side, the north side of this magnet over here, is going to repel the north magnetic field that we're going to have created by the current over here, and then it will, as it rotates, it will become attracted to the south side, and then the current is going to flip. Alright, so if that's too much information, I'm going to come back to this and I'm going to break this down. So let's go back and start from the beginning, so to speak, and so you can all understand what's happening here. So let's imagine just a simplified form of this, and we'll move away from that GIF animation for a while. And let's think about, imagine you have a magnet, and the magnet is on an axle, so it's free to rotate. And if you imagine a second magnet over here that's held stationary, and we just essentially bring one magnet close to the other magnet, what do you anticipate would happen to this magnet on the left-hand side given the scenario that we have right here? Well, you could say the south pole over here is going to repel this south pole over here. This magnet, we'll say, is stationary, but this magnet can rotate. So this magnet would rotate either clockwise or counterclockwise such that the south side would rotate away from the other south side. And the beginning of this process, as we go from, say, this stage right here all the way down, you can imagine that there is a repulsion in the beginning here, but as we get further down, there's also this attraction over here. So this north side is being attracted to the south side, and then you end up with something like this. So that would be pretty straightforward, something we would anticipate would happen if it could happen. Alright, now let's imagine that we flipped the north and south pole of this magnet somehow. What would happen? Well, if we flipped it sort of just magically for a moment, I'll explain how it does get flipped in a moment, but we'll just say if we flipped it somehow, then the process would repeat itself, right? You would end up with this process again. And in the meantime, we could ask ourselves, well, what is happening? Well, what's happening is you get rotational motion based on this magnetic interaction that's happening here. And if we could somehow harness that, that would be incredibly useful. All right, so we're going to build on that concept. We're going to say the same kind of thing happens over here. It's going to flip one more time. But now let's compare what we have here with, instead of using a permanent magnet like we have over here, let's use an electromagnet. So an electromagnet just has an iron core, and then it has a coil of wire, and the current is going to flow through from one direction to another, and it creates a magnetic field that's actually very similar to a permanent magnet, actually. So the magnetic field lines would come out over on this side and come back in on the south side, and the two north poles would repel each other. And so let's use these ideas here and just substitute in the idea of an electromagnet. Alright, so then you would say, well, if it were somehow able to rotate, we would have the same thing happen that we had before. Now, you might start to anticipate some problems here. So one problem would be, well, the wires would get tangled up, right? Like, that would be a problem, and then you would need to instantly switch the north end and the south end of the poles to keep the rotational inertia going. But if we could, then you could cause something to continuously rotate based on electrical power, which would be amazing. Now, these two problems are able to be overcome, so let's talk about how they are overcome. So now we're getting closer to reality in terms of what actually happens with an electric motor. I want you to imagine, again, we've got a permanent magnet over here and a permanent magnet over here. They're called stators, and you can think of part of that word having to do with static magnets here that are used in motors. And then you could say, well, we've got our power source right here, that's going to be a battery. You've got a current that's going to flow through. We'll assume conventional currents that goes through this way all the way around to the negative side of the battery. You've got our brushes here in yellow and our commutators here in these two colors right here and right here. And so what's going to happen is that current flows through and it creates a magnetic interaction where you're going to have repulsion on this side between this wire right here and this north pole of this static magnet on the left hand side. And so this is going to start to rotate, and what happens is about halfway through the cycle, notice that the commutators are not touching the brushes for a brief moment of time. When they do come into contact, they're going to look like this again, and that will actually change the direction of the currents such that it's continually going to be working in this way, meaning like you're going to have current flowing here that will repel this north side of this static permanent magnet over here. And every time you have a flip of the currents, because of the very clever way it's set up, that rotational motion will continue. And what that means is you can get rotational motion and rotational energy out of electrical energy. So that's what an electric motor does, is it uses electrical energy and converts that into rotational energy. You could say rotational mechanical energy, which is then converted into all kinds of useful applications that we have throughout our modern life. So pretty amazing stuff. These concepts really do underlie all of our modern society. In any case, if you think about all of the amazing things that electric motors are able to accomplish in your everyday life, it's actually pretty amazing. So hopefully this has been helpful. If you have any comments down below, please let me know. And I hope you all have a great day. Take care.